Hopefully you have this written down for yourselves. We're going to do the first couple steps to make sure everybody's on the right track. Now, there's nothing wrong with like plugging 5 in, or have to factor this and stuff. So kind of double check to make sure that that is actually true from the beginning. Because if it's not true, then I'm not going to prove that. I'm going to say, no, it's not true. Screw that. So my side work. Now, please understand, I did say that if you're going to turn a proof in, you wouldn't even show your side work. You're going to turn this proof into like a mathematical paper or whatever. Your side work is figuring out the delta that works in reaction to the epsilon. Right? And then the proof is when you use that delta you found. I want to see the side work. I'm a teacher. I want to make sure it came from the right place. Cool. So show me that. So to do the side work, we start with where I want to end up, which is why it feels like we're cheating. We're just kind of investigating the problem. That's why it's on the side. So I fill in, what is f of x? And what's L, supposedly? 20. So you do the same thing, especially with linear functions. You just work with this until you capture the delta statement, the x minus a less than something. Because now you can just compare it. Whatever you end up with here is what you let delta equal. Technically, it could be even smaller than that, but you let it equal that. So, of course, this I can work with, right? You end up with 2, right? X plus 5, x minus 5, x minus 5 is canceled, so you end up with this. Cool. So you get 2x plus 10 minus 20. And if you divide by 2, I'm doing a few more than just the first couple steps. That is all side work. None of that is the proof yet. That is just constructing our delta. So the proof is use the delta to show that what's supposed to happen happens. And when I ask you to do this kind of problem, I don't want to see just symbols and numbers. I need to see some writing, because that's the proof, right? You got to tell me what the hell's going on. So the proof now, here's the real proof. Put this stuff in like dotted, whatever kind of sound effects you're using. Let delta equal. Then when x minus 5 is less than, is less than delta. Now you just start doing, replace delta with what you want it to be, right? And then, this is another reason why it feels like cheating. You just do everything you did over there in reverse. I like it. So it really, real quick, it doesn't matter what delta is. What matters is I'm able to find a value for delta that works, no matter what epsilon is.
So that's after midway through doing it back, how do you make it into
All right.
the 2x?
You ready? So what do I do next? This is ultimate feeling like cheating. I can basically just, I really can honestly just copy that shit down. Now, you have to not just believe, but you have to understand that I am doing, isn't this equal to 2x plus 10 minus 20? Isn't that true? And isn't this 2 times x plus 5? And then can't I multiply top and bottom by x minus 5? What would tell me to do that? Well, I already kind of know how to build it back up because I knew how to tear it down, right? So that's basically f of x minus L. Therefore, that's the proof. We showed. We had to show that when this is true, then this is true. We just showed it. Starting with this, we get this. So when this is true, bam, we're done. You say, done. But I really, now, you can get lost in the weeds a little bit. What's important to me about this section is understanding what the symbols mean, understanding what they tell you about limits. This whole idea of distance away makes complete sense. It's really what a limit is. What do I mean when I have a horizontal asymptote at 3? What the shit does that mean? You guys remember? Can they go through it? All day long. I can go through it an infinite number of times. Real quick, vertical asymptotes come from the domain. You can't go through those. Because they say these x's suck. They make my function freak out. Horizontal asymptotes are what happens when x gets really big. Positive or negative, right? So what happens when x is not so big? Any damn thing it wants to. So I could have a function that goes through an infinite amount of times. Just what has to happen? Eventually, they have to get arbitrarily close to 3. The outputs do. That idea of close always comes up naturally when you're talking about limits. You're going to eventually have to get closer to that thing if that really is the limit. If you don't ever get close to it, that ain't the damn limit. Right? This I like. This is a pluck a guitar string. Thankfully, it's dampened, or else every guitar would still be going. Right? Hey, how are you? I just love that idea. All the guitars are still going that have ever been strung. But thankfully, there's dampening forces. They eventually shut the hell up, right? Mathematically, this would never have an amplitude of 0, but in the limit, it does. Is that cool? Yeah, I like that. Remember, you can go through horizontal asymptotes. They're suggestions that you only eventually have to do. Vertical ones are like, it's a trap, pull up. You can't go through that. Like that. Okay. I think a real quick visual I want to show you. Can you guys shut those lights off again? Thank you. Like, I thought the back of the room would be a good place to sit. It's gotta work. Okay. I can't remember which one of these I signed for homework, so maybe I'm doing a homework problem right now. So maybe you want to take good notes. But I love this visual. So, what's epsilon in this problem? What's epsilon? Now be careful, epsilon is not a range, it's a distance. So how far away do I get on either side from 2? 0.5. Remember, you can see right there 2, right? Isn't that f of x minus L less than epsilon? Epsilon goes with the outputs. So epsilon is 0.5, that's why they're 0.5 up, 0.5 down. Now, if I trace 1.5 over, I can see what that input is. If I trace 2.5 over, I can see what the input is. So what's delta? The distance away from 3 so that the outputs are always in between here. Could delta be 0.8? Because then what would that mean? I have to go 0.8 down. Is that inside here? No, that is way the shit down there. Do you see what I'm saying? So what would delta be? It's not 0.8. 0.4. I really want this to make sense. This way, I can go all the way to 3.8 and still be good. But this way, I can only go to 2.6 and still be good. So I can't say delta is 0.8 because it's got to work in both directions. So delta is 0.4. If I go to 3.4, does it still work? Oh yeah, I'm still in there, right? All I need is a delta that keeps me in there. So delta could be smaller than what I find. It just can't be bigger. Right? Let's try one out. Ooh, oh shit. Right. Here we go. Here's the ultimate. I'm definitely going to let you out of here, but after this. I'll let you out of here a little early. If you don't have a calculator, I'm sorry. You should get one from the help. We set up a situation first. Let's do, I think there's a, here we go, perfect. All right, let's look at this guy. So now watch. What is my f of x in this problem here? What's my f of x? What's f of x? Tangent, right? X minus a less than delta. F of x minus L. Oh, f of x must be tangent. Are you guys able to pick out the parts? Yeah, I like it. My input's related to delta, my output's related to epsilon, so that tangent x must be the function. What's the supposed limit? 1. As x goes to what? What's a? Pi over 4. So as the x's get close to pi over 4, because what's delta? Delta is like another name for close. As the distance between x and pi over 4 gets small, as they get close to each other, then the outputs have to get close to 1. They specifically wanted to be within 0.2 of 1. So it's the same as the problem we just did where they had the graph already, but now we got to make our own freaking graph. I'm going to show you how to do that. We know how to make a graph tangent. You just tell it, make tangent. Cool. And I could be kind of, well, let's see. Just to make sure everybody has the same graph, if you're playing along with me, hit zoom 6. That's the zoom standard. Makes a standard window. Okay, I like it. Now, let's see. There's tangent. Now I want, let me move that over for a second. Okay. I want my stuff to be, if I work with this just a little bit, I want tangent x minus 1 to be like this. So I want tangent x to be between 0.8 and 1.2. Is everybody cool with that? Alright, anyway. Listen now, watch this, watch this. So here's how I kind of recreate this. First off, let's kind of, alright, there's several things I'm doing here. Is everybody cool so far with what's happening? Because I've got a graph of tangent x, and now I know what I want tangent x to be between. What input am I curious about? Around what input? Pi over 4, right? So let's do this. If you're playing along with me, make your window go from 0 to pi over 2, so that pi over 4 is right in the middle. Of course, what's happening over here, pi over 2 is where the asymptote is for tangent, right? Is that cool? All right, stop. You guys decent? Because what's tangent of pi over 2? It's sine of pi over 2 over cosine of pi over 2. What's sine of pi over 2? 1. The sine likes y. What's cosine of pi over 2? 0, right? Because there's no x piece to this. So 1 over 0 is positive. 1 says positive infinity. That's what it's doing there at the end. Is that cool? Because I made my upper x pi over 2. So that's going up towards the asymptote at pi over 2. I like it. So pi over 4 is right in the middle, between 0 and pi over 2. Now, watch. If I want tangent to be between these two, so I'm trying to reconstruct this picture. And see how these are, see how this is 2.5, this is a straight line, right? So what I can do is I go back to y equals and I make this 0.8, and I make this 1.2. Now there's going to be straight lines at 0.8 and 1.2. So I really am recreating that graph they made for me. Ooh, now look at that. All right, so how can I improve this picture? So I'm also trying to do a little graphing calculator workshop with you guys. What? This picture sucks so bad, but right? I mean, everything's happening like here. It's like, holy shit. So maybe I want to make my outputs go from 0 to 2 or something. You guys see? So I want to zoom in a little bit. So I want to make my outputs go way the hell up to 10. Do I need that shit? Do I care about up here? I care about down here. What did we do in the book? Didn't we look over and go down, look over and go down and see what the inputs were? That's what I want. I want to look over and go down, look over and go down, but I can't do that because everything's happening there. So I want to blow that up a bit. So if I go back to window, I can make my outputs go from 0 to flush. Let's see what this looks like. There's the floor. There's the ceiling. So now I want to draw these. I want to figure out what the x's are. Anybody have any idea how to figure out what this x is here? What is that x?
Oh,
Intersect. You can use all the top row is graph stuff. So the one place where it says calc above trace, that means graphically calculate something. So if I do second trace, I can calculate the value at some point. Where is it? Hit the x-axis, a min-max. So 6 and 7 are the two things we learn in calculus: derivatives and integrals. So you can just look at it and go, oh, that's nice. So do 5 for intersect. And I don't know if you guys have ever done this before, but it's going to ask you 3 questions. What is your name? What's your favorite color? What is your quest? So, where's my first curve? Okay, it's that one. My second curve is that line there. And my guess is right where the cursor is. So there, 0.675. We'll round it. They write it up here. So we got 0.675. So again, I really want you guys, what are we doing right now? We are recreating this idea. We had to figure out where that is. We just did. What about the other one? Figure out the other one. The other intercept up here. So you can bring it down and figure out where that x is. You have to hit up to get to the other. Make sure you get to this black line here, this top line. Make sure you're on that top line when it says second curve. Enter. And then my guess is right there. So you should be getting 1876. What is my A? What's my number in the middle? It's pi over 4, right? And pi over 4 is roughly, what are you doing, Jeff? It's 0.78 something, whatever. Check me on that. Please do. Is it 0.78 or point? What is it?
Oh, wait, no.
Pi divided by 4. Yeah, okay. So how do I figure out what delta is then? The same way we did earlier. I see how far this is away from pi over 4, and I see how far that is away from pi over 4, and which one do I pick to be delta? The one that is smaller, so that it makes sure that I stay in there. So in the calculator, you just do pi over 4 minus 0.876. Pi over 4 was well, it doesn't matter. If you do this, you get negatives, but please, dear God, tell me you can handle that. Make this positive when you do this, and see which one is smaller. So if I do pi over 4 minus 0.876, positive 0.09, and pi over 4 minus, who was it? 0.675. So I'm going to make delta 0.09. smaller one so that it always forces to be inside that range. So I did assign, I might have assigned that problem, so I might have just done one for you, but hopefully I didn't. We'll see. All right. So we did 2, 3, 2, 4, 2, 5 today. That quiz on Thursday, right? We'll probably have another quiz next week. We'll talk about it on Thursday. We'll get into 2, 6. If you remember your asymptote stuff from pre-calculus, your horizontal asymptote stuff, a big part of 2, 6 is all about that. It's about infinite limits. Cool. So we got here nice and early today.